Didn't study for AP Physics 1? That's okay. This video's got everything you need to know. Hopefully, you get a 3. Let's get right into it. Unit 1, Kinematics. There's these 5 equations. They're called the Big 5. You really need to know them. Each of them is missing one variable that you might see in a problem, which is perfect because if you don't see that variable in the problem, use that equation. It's that simple. If you're in free fall, well, that's perfect. Your acceleration is 9.8 meters per second because that's the acceleration of gravity. Sometimes just use 10 meters per second because that's faster. Moving on to graphs. I'm not a calculus student. How am I supposed to understand this? That's okay. I'm going to teach you right now. Slope of a position versus time, that's velocity. Slope of velocity versus time, that's acceleration. Area of a velocity versus time graph, that's displacement. Area of acceleration versus time, that's change in velocity. Alright, moving on. Unit 2. This is our friend Newton. He wrote a book called Principia a long time ago. Doesn't matter. All we gotta know are his 3 laws. First law. Something that does not have a net force acting upon it ain't gonna change. If it's not moving, it's gonna stay not moving. If it's moving at a constant speed, it's gonna stay moving at a constant speed. Don't be tricked. If I push on a block, is it gonna move? Sometimes. Because if there's friction, then there's no non-zero net force and the block doesn't move. No friction, the block moves. Alright, moving on. His second law. Net force on a object is equal to the acceleration times the mass of that object. Also works for systems too. Net force on a system equals acceleration of the system times mass of the system. This is really helpful in those Atwood machine problems. So all you gotta remember is F equals ma. If AP Physics was a Madden video game, this would be on the cover. Lastly, Newton's third law. You've probably heard this one everywhere. Forces come in pairs, right? Yep, that's correct. I push on you, you push back on me with the same amount of force. If I exert a force of 10 newtons on this block, it's exerting a force of 10 newtons on me. Throw a watermelon off a skateboard, you actually move. Isn't that crazy? Next, don't miss up mass and weight. Weight is a force. It's equal to your mass times the acceleration of gravity, g, which is 9.8 meters per second or 10 meters per second, like I said earlier. Next force you gotta know, it's called the normal force. It's the force that acts perpendicular to the surface that it's resting on, which is not always flat to the floor. Always remember that the normal force is perpendicular to the contact surface, not the ground. However, if it is flat and parallel to the ground, just remember normal force is exactly opposite in direction of weight and is equal in magnitude. Now that you know all these forces, make sure you know how to draw a free body diagram, which is basically you draw the thing and then all the forces acting on it. So you got a block sitting on the ground, well, you got the normal force pointing up and the weight force pointing down. Exact same size, just opposite in the direction. Another force you gotta know, it's called friction. It's equal to the normal force times something called the coefficient of friction. There's 2 types of friction. You got static friction and then you got kinetic friction. Makes sense, right? Static friction, the friction of not moving. Kinetic friction, the friction of moving. Pretty easy. Remember why that block I talked about earlier didn't move? That's right, because it had static friction. However, if I push a little harder and it starts moving, well, now it's kinetic friction. To sum up, if you're looking for the acceleration of the system, like you got a pulley, make sure you always label forces going in the direction of motion, and then you use that fancy F equals ma formula to find the acceleration. Moving on, Unit 3, uniform circular motion and gravity. If you didn't know, there's this force called gravity that Newton discovered when an apple fell on his head. Before we get to that, we gotta realize that sometimes things like to move in circles. This is called uniform circular motion. Notice the uniform, that means it's moving at a constant linear velocity. However, there must be some sort of force making it go in a circle, right? Yup, that's right. It has something called centripetal force, which points directly to the center. Notice how that is perpendicular to the velocity. It is given by mass times v squared over r. And you might be wondering, that looks an awful lot like our F equals ma equation. And that's right. This tells us that its acceleration towards the center, called centripetal acceleration, is equal to velocity squared over r. Now, what does this have to do with planets? Well, if you didn't know, planets like to move around other things. Usually, it's a pretty close to a circle. And remember our buddy Isaac Newton? That's right, he came up with the law of gravity. It's called universal gravitation. It tells us that between 2 big bodies, or any bodies, that the force of gravity between them, that they act on each other, is equal to big G times mass of the first one times mass of the second one over the distance between them squared. You might be wondering, what the hell is big G? Well, honestly, he didn't know either, but turns out it's this constant that is equal to 6.67 times 10 to the negative 11 Newton times meter squared over kg squared. That's a mouthful. Don't need to remember it. It's given to you. You're gonna get a lot of satellite problems. Make sure you know this one by heart. Another nice little equation to know is potential energy that is from gravity at far distances. This is equal to G times m1, m2 over r. That's it. Moving on to the big unit. This is energy. This entire huge unit can be broken down to one connection, the work energy theorem. This thing is the second cover of our Madden game. To put it simply, energy is the ability to do work, and work is the change in energy. Let me give you an example. Everything's got kinetic energy, right? Well, not if it's not moving. So if I have a block at rest and I do some work to it, soon at the end, the amount of work I did to it is equal to how much kinetic energy it has. Boom, work energy theorem. Other type of energy you gotta know, potential energy. We'll get to springs later, but right now the only potential energy you need to know is gravitational potential energy. And at the surface, it's pretty much just equal to mgh. That's all you gotta know. Remember that energy can be transferred and it has to be conserved in a system. So if you drop something, all that kinetic energy is coming from all the potential energy it had. It just doesn't come out of nowhere. You might be asking, how do I even know how much work I did? Well, that's pretty easy. Just take the force you applied on average over that entire distance and multiply it by the distance. That's right, force times distance equals work, work equals change in kinetic energy. Kinetic energy is given by 1/2 mv squared, and potential energy is mgh. Gotta remember those two as well. One last thing the AP wants you to know, it's called power. I've literally never seen a power problem in my entire life doing worksheets for AP, but they want you to know it anyway. It's basically just how much work you do over time, right? So basically it's in terms of watts. There's this guy, his name's Watt. I think he's on the Steelers. He probably came up with this. To be fair with you, I'm not even sure, but that's all you need to know. Moving on. Momentum. This is a big unit too, but don't worry, because I got you. Momentum, pretty easy formula. It's just mass times velocity. Or you can think of it as force times time. That's another pretty important one too. That's called change in momentum. If you start from 0, you have 0 momentum. If I apply a force for some time, well, I have that much momentum now. Boom, change in momentum. It's also called impulse. Just remember that. Remember, momentum is always conserved. You should have learned this. But if two things smack into each other, to find the velocities, you just got to remember, momentum before is equal to momentum after. However, like I said, only momentum is conserved. Kinetic energy is not conserved in collisions all the time. It's only in an elastic collision that kinetic energy is conserved. In an inelastic collision where they stick together, a lot of kinetic energy is lost. So you can't add it up to the original kinetic energy anymore. And always remember, momentum is not a scalar. It's a vector, while kinetic energy is a scalar. Moving on, simple harmonic motion. This one sucked. I hated this unit. But basically, two formulas you gotta know. Period of a spring, period of a pendulum. Right here, all you gotta know. Next big name you gotta know, Hooke's law. Force of a spring is equal to the spring constant times the distance. That's what simple harmonic motion even means in the first place, that the restoring force is proportional to the displacement. Some key terms. Amplitude, the furthest you will get away from equilibrium. Equilibrium, the resting position or center where x is 0. Next thing you gotta know, there's our springs that have potential energy. Springs store energy. Well, how do I know what the spring potential energy is? Well, I got you. It's equal to 1/2 k times the current displacement squared. Alright, we're in the home stretch. Final unit. It's torque and rotational motion. This was arguably even worse than the last unit, but it's okay because I'm here to give you all the things you need to know. Rotational kinematics, really similar to linear kinematics. Here's what you gotta know. Force is equivalent to torque. Mass is equivalent to moment of inertia or rotational inertia. Acceleration is equivalent to angular acceleration. Force equals mass times acceleration. Well, we got that too in rotational kinematics. Its torque is equal to I times alpha, which is moment of inertia times angular acceleration. Got velocity in linear kinematics. We got velocity in angular kinematics. It's angular velocity. That's all you need to know for now. Everything I just mentioned can be applied to the big five kinematics equations directly. One for one, what I just said was equivalent will work as a big five problem, but for angular instead of linear. Next thing you gotta know, things have center of masses. Do you need to know how to calculate where it is of some random object? No, you don't, but it's good to know that a center of mass is usually where it's rotating about. No, the center of mass isn't always actually in the object. It can be outside of the object. It's simply where the average of all the mass is. If you put a stick and you stuck it out, that's where it would balance. Alright, the biggest topic in this entire unit is torque. Like I said earlier, it is the equivalent of force, but for rotation. It is equal to a force times the distance to the center of rotation. So force times the lever arm is equal to torque. Next, you got equilibrium. Like I said before, there's equilibrium in terms of springs and translational kinematics, where the forces are all canceling out and you get zero. It's at the initial position, right? Or it's not moving. Well, in rotational kinematics, it's pretty much the same. It's when the net torque is equal to zero. So everything cancels out really nicely and you're in equilibrium. You're going to get a lot of these problems. Just make sure that the torque going one way is equal to the torque going the other way. That's all you got to know. Remember regular momentum? Well, there's angular momentum too. It's denoted by big L. And this time it's equal to the rotational inertia or moment of inertia times angular velocity. Doesn't that look pretty similar to the regular momentum one? Yup, that's right, because it's all the same stuff. Just like for regular momentum, the change in angular momentum is equal to torque times time. Just like how regular momentum has a change equal to force times time. And we're done. Congratulations. Hopefully with all this information you can go study and you can get a 3 on this exam. I hope everyone does the best they can. I'm honestly kind of stressing out for this exam because I didn't study, but I guess making this was a good way to study. Everyone have a great night. Go do your Princeton review books, your Barron's book, your 5 Steps to a 5. Go have fun. Get a good night's sleep before the test. And yeah, make sure to bring a graphing calculator. They let you do that now. Make sure to bring 2 pencils. They've only let you do that ever. And bring a snack, bring water, all that good stuff. Hopefully your physics teacher is nice and lets you camp out in his room or something.